Picture the universe in its infancy, a time before galaxies, before stars, before even the atoms that make up our bodies existed. There was only darkness, an all-encompassing void, until something incredible happened. The very first light elements began to form, the fundamental ingredients of everything we see around us today. Those initial moments, those first particles, hold secrets that have puzzled scientists for generations. How did it all begin? What forces were at play in the universe's earliest seconds? And why does the answer to these questions matter to us right here and now? We're about to explore 30 remarkable theories about the universe's first light elements: hydrogen, helium, and lithium. These weren't just random substances, they were the building blocks of reality itself, the starting point for every star, every planet, and every living thing. Each theory we'll discuss opens a door to a different possibility, a different version of how our cosmos took its first breath. Some ideas are widely accepted, while others challenge everything we thought we knew. But all of them invite us into a mystery that stretches across nearly 14 billion years, connecting each of us to the very origins of existence. This journey isn't just for scientists or astronomers, it's for anyone who's ever looked up at the night sky and wondered how it all began. By the end of this video, you'll have a deeper understanding of where we come from, and perhaps even a new sense of wonder at the extraordinary story written into the fabric of space and time. So let's dive in together and uncover the astonishing theories behind the universe's first elements. Our journey begins with the most established and widely supported explanation, often called the cornerstone of modern cosmology: Big Bang Nucleosynthesis. To truly appreciate this theory, we need to rewind the cosmic clock to a period almost unimaginable in its extremity. We're talking about the universe when it was merely 3 minutes old. At this point, it wasn't empty space. It was an unimaginably dense, searingly hot primordial soup. The entire cosmos was crammed with a raging plasma of fundamental particles, protons and neutrons zipping around at incredible speeds, constantly colliding in the incredible heat. But as the universe expanded, it also cooled, and this cooling was the key that unlocked the door to creation. Around the 1-second mark, the temperature dropped just enough for those free-flying protons and neutrons to begin sticking together when they collided, forming the first atomic nuclei in a process called nuclear fusion. This wasn't a slow process, it was a frantic 3-minute burst of cosmic alchemy. Protons and neutrons paired up to form deuterium, a heavy isotope of hydrogen. Once deuterium was available, it acted as a stepping stone, rapidly fusing with more particles to form helium nuclei. Trace amounts of lithium also began to form in this frantic rush. Now, why did this process only last for those first 3 minutes? Why didn't the entire universe just fuse into heavier and heavier elements right then and there? The answer is one of the most elegant parts of this theory. The universe was expanding too quickly. As it grew, the density of the particle soup plummeted. The particles were simply spreading out too far, too fast. The average proton or neutron suddenly found itself alone, with no other particles nearby to collide with. The temperature had also dropped below the critical threshold needed to overcome the electrical repulsion between positively charged nuclei. Fusion slammed to a halt, freezing the elemental composition of the universe in place. According to this model, the cosmos was left with about 75% hydrogen and 25% helium by mass, with just a tiny fingerprint of lithium, a prediction that matches what we observe in the oldest, most pristine corners of the universe almost perfectly. This remarkable agreement between prediction and observation is a huge part of why Big Bang nucleosynthesis remains the gold standard for explaining the origin of the first light elements. Yet for all its success, the standard model of Big Bang nucleosynthesis isn't a perfect, airtight story. While its predictions for hydrogen and helium are spectacularly accurate, the amount of lithium it forecasts doesn't quite line up with what we observe in the ancient stars of our galaxy. This is known as the cosmological lithium problem, and it's a small but persistent mystery that has led some scientists to ask a profound question. What if the early universe wasn't quite as smooth and uniform as we've always assumed? This brings us to our second compelling theory, the inhomogeneous Big Bang model. This theory proposes a cosmos with a more textured, lumpy beginning. Instead of a perfectly smooth primordial soup, imagine the universe had pockets of intense density right from the start, regions that were much hotter and more crammed with particles, swirling alongside vast, emptier voids. These variations wouldn't be random. They're thought to be the amplified echoes of the tiniest quantum fluctuations, those microscopic bubbles of energy that popped in and out of existence in the first fraction of a second. As the universe expanded exponentially during a period called inflation, these infinitesimal wrinkles in spacetime were stretched into colossal density variations across the cosmos. How would this landscape of hills and valleys in density change the story of nucleosynthesis? The answer lies in the local environment. In those incredibly dense, hot pockets, nuclear fusion would have been far more efficient and frantic. The higher density means particles are colliding much more frequently, potentially allowing for the creation of more helium and even minute amounts of heavier elements like beryllium or boron in those specific regions. Conversely, in the less dense voids, the process might have been less productive, leaving behind a different mix. When everything finally expands and these pockets mix together, the overall average abundance of elements we see today could be a blend of these vastly different local outcomes, potentially accounting for that puzzling lithium discrepancy. The appeal of this model is that it introduces a dynamic and chaotic birth for the universe, one where your location in the cosmos in those first few minutes dramatically influenced what elements were forged around you. It suggests that the first seeds of the large-scale structure we see today, the vast cosmic web of galaxies and clusters, were already imprinted before the first atoms ever formed, guiding the very construction of reality from its earliest moments. While still a speculative alternative to the Standard model, the inhomogeneous theory challenges us to reconsider the simplicity of our cosmic origins and reminds us that even the smallest quantum whisper can have a billion-year echo. This brings us to a theory that pushes our understanding of those initial conditions to the absolute limit, examining an event so profound it arguably set the stage for everything that followed. We're talking about cosmic inflation and its potential impact on the universe's first elements. To grasp this, we need to venture even further back in time, to a moment almost inconceivably brief. The universe was only a tiny fraction of a second old. The leading theory suggests that at this instant, a peculiar form of energy embedded in the fabric of space itself caused the entire cosmos to undergo a period of hyper-fast, exponential expansion. In less time than it takes to blink, a region smaller than a subatomic particle was stretched to a size larger than our entire observable universe today. This wasn't just a simple zooming out, it was a fundamental reshaping of reality. The inflation theory was originally developed to explain some of the universe's large-scale features, like why it appears so uniform in temperature from one distant end to the other. But its implications for the first moments of nucleosynthesis are equally fascinating. The end of this inflationary period is thought to have released an enormous amount of energy, reheating the universe and repopulating it with a fresh, hot plasma of particles, the raw ingredients for the Big Bang nucleosynthesis that would begin moments later. In essence, inflation didn't just stretch space, it may have also determined the initial conditions for the entire nucleosynthesis process. So how could this rapid expansion have left a fingerprint on the first elements? The key lies in the gravitational waves and density fluctuations that inflation is predicted to generate. These are not waves in water, but ripples in the very fabric of spacetime itself. Some models suggest that these primordial ripples could have created minute variations in temperature and density across the universe as nucleosynthesis began. These weren't the large-scale hills and valleys of the inhomogeneous model, but far more subtle and universal textures. These tiny fluctuations could have slightly altered the rates of key nuclear reactions during that crucial 3-minute window. For instance, a local infinitesimal change in density might have allowed a few more lithium nuclei to form or be destroyed, potentially offering a solution to the lithium problem that is deeply rooted in the physics of the universe's very first instant. The most compelling aspect of this idea is its testability. The specific pattern of gravitational waves predicted by different inflationary models could, in theory, be imprinted on the polarization of the cosmic microwave background radiation, the afterglow of the Big Bang. By building incredibly sensitive telescopes to study this ancient light, cosmologists are hunting for the faint signature of these waves. If detected, it wouldn't just confirm inflation. It would provide a direct link between the universe's most rapid expansion and the precise abundances of the elements we see today. This theory challenges us to see the first elements not just as a product of the first 3 minutes, but as a cosmic message from the first trillionth of a second, a relic of the most violent and transformative event in all of existence. To truly grasp the very beginning, we must push our imagination even further back than that primordial particle soup. Before there were protons and neutrons, before there were even atoms or atomic nuclei, the universe was in a state so extreme that the very components of matter as we know it were utterly broken apart. This leads us to our fourth theory, which focuses on a fleeting and bizarre phase of existence known as the quark-gluon plasma. For the first few millionths of a second after the Big Bang, the temperature and density of the cosmos were so astronomically high that protons and neutrons, the workhorses of Big Bang nucleosynthesis, couldn't even exist. The forces that normally bind them together were completely overwhelmed by the sheer energy. Instead, the universe was filled with a seething, exotic soup where the fundamental building blocks of protons and neutrons, quarks and gluons, roamed completely free. This is the quark-gluon plasma, a state of matter that physicists have actually recreated in powerful particle colliders like the Large Hadron Collider, giving us a glimpse into the universe's most extreme conditions. The critical moment for our story of element formation is the transition out of this plasma state. As the universe continued to expand and cool, it eventually crossed a threshold where the energy finally dropped low enough for quarks and gluons to suddenly snap together, like a phase change from a gaseous vapor into liquid droplets, forming the first protons and neutrons. This process is called hadronization, and it happened across the entire cosmos in an instant. But here's where the intriguing possibility lies. What if this transition wasn't perfectly smooth and instantaneous everywhere? Some theories suggest there could have been slight delays or variations in how this cooling occurred. If certain regions of the quark-gluon plasma cooled or expanded at slightly different rates, it could have led to small fluctuations in the final number of protons versus neutrons that were frozen into existence. This ratio is absolutely critical because it directly determines how much hydrogen versus helium you end up with. A universe with even a tiny fraction more neutrons would produce significantly more helium during nucleosynthesis. Conversely, a few more protons would leave behind more hydrogen. These subtle initial imbalances from the quark epoch could be the hidden reason behind the slight anomalies we see when we look at the oldest stars, potentially offering another explanation for puzzles like the lithium discrepancy. It suggests that the story of the first elements wasn't written only during the 3 minutes of nucleosynthesis, but was actually predetermined by the chaotic physics of the universe's first millionth of a second. Now we turn to one of the most fascinating and speculative ideas on our list, a theory that introduces a truly dramatic character into the early cosmic drama, the primordial black hole. Imagine if, scattered throughout that searingly hot infant universe, were not just particles of matter, but countless tiny, incredibly dense gravitational traps. These wouldn't be the massive black holes formed from dying stars that we know today, but microscopic ones, some no heavier than a mountain yet smaller than an atom, theorized to have been born from the intense density fluctuations in the very first second after the Big Bang. The potential influence of these primordial black holes on nucleosynthesis is a twofold mechanism, starting with their immense gravity. Even a microscopically small black hole possesses an incredibly powerful gravitational field for its size. In the dense early universe, a cloud of protons and neutrons passing near one of these objects would have been accelerated to tremendous speeds. This isn't just a minor effect, it could have fundamentally altered the nuclear reactions happening nearby. Fusion requires particles to collide with enough force to overcome their mutual electrical repulsion. By acting as natural particle accelerators, these black holes could have dramatically increased the rate of collisions in their immediate vicinity, potentially creating localized hotspots where fusion happened faster and more efficiently than in the rest of the universe. One region might have produced an overabundance of helium, while another could have seen the creation of elements slightly heavier than lithium, all because of the gravitational influence of these tiny, ancient objects. The second, and even more exotic, mechanism is Hawking radiation. Stephen Hawking theorized that black holes aren't completely black, they should slowly lose mass and evaporate by emitting radiation. For a stellar mass black hole, this process is immeasurably slow. But for a primordial black hole with very little mass, the story is completely different. These tiny entities would have evaporated fantastically fast, releasing their entire mass energy back into the universe in a violent burst of radiation and particles. If a significant number of these black holes evaporated right during, or just before, the 3-minute window of nucleosynthesis, they would have flooded their local environments with a huge wave of energy and extra particles. This sudden injection could have seriously disrupted the delicate ballet of nuclear fusion. It might have provided the extra energy needed to break apart freshly formed deuterium nuclei, creating a bottleneck that limited the production of helium. Alternatively, it could have provided the seeds for forming more lithium or even trace amounts of other light elements. The evaporation of these black holes would have been like tossing a handful of rocks into a calm pond. The ripples and disruptions could have left a permanent, if subtle, mark on the cosmic elemental abundances we measure today. While firmly in the realm of theoretical physics, this idea is compelling because it offers a potential solution to several cosmological puzzles beyond just the lithium problem. Some researchers suggest the gravitational lensing effects of these ancient objects could explain the mysterious dark matter that holds galaxies together, while their explosive deaths might be the source of some of the most high-energy events we detect in the cosmos. The primordial black hole influence theory challenges us to consider that the first building blocks of matter might not have been forged in a uniform furnace, but in a chaotic cosmic landscape dotted with the most extreme gravitational phenomena, where the echoes of their existence are literally woven into the atoms that make up our world. This leads us to a theory so profound it challenges the very bedrock of physics itself. What if the rules of the game weren't always the same? The variable constants theory proposes a radical idea that the fundamental forces of nature, the numbers we treat as unchanging laws, might have been slightly different in the universe's explosive first moments. Constants like the fine structure constant, which governs the strength of electromagnetism, or the gravitational constant, might have been slowly shifting as the cosmos expanded and cooled. Consider the fine structure constant for a moment. In our universe today, this number precisely dictates how strongly protons repel each other. That repulsive force is the main barrier that nuclear fusion must overcome to create new elements. Now, imagine if that force was just a fraction weaker in the past. the electrical barrier between nuclei would have been lower, allowing fusion to happen more readily and efficiently during Big Bang nucleosynthesis. This could have led to significantly more helium production and potentially less lithium. Conversely, if the constant was slightly stronger, fusion would have been even more difficult, potentially leaving us with a universe much richer in hydrogen and devoid of any helium at all. The observed abundances of hydrogen and helium are so perfectly poised that even a tiny deviation in these constants would have resulted in a cosmos unrecognizable to us, one that might never have been able to form stars or planets. The evidence for this staggering idea is debated but compelling. Some observations of distant quasars whose light has traveled for billions of years to reach us suggest the fine structure constant might have been minutely different in the past. These measurements are incredibly difficult to make and are hotly contested within the scientific community. Critics point out that potential systematic errors in the observations could easily mimic such a subtle effect. Furthermore, if constants like these were truly variable, it would require a major overhaul of our most fundamental physical theories, including general relativity and the standard model of particle physics. Most physicists maintain that these constants are truly constant, as there is no widely accepted mechanism within established physics that would allow them to change. Yet the possibility remains a tantalizing frontier. It suggests that the first elements we see are not just a product of the early universe's conditions, but a permanent record of the laws of physics themselves settling into their current, stable values, freezing the cosmic constants into place at the same moment the first atoms were born. While the story of the first elements often focuses on protons and neutrons clumping together, a far more elusive and mysterious family of particles was also swarming through the early universe, potentially holding the keys to the final abundances we observe. This brings us to the lepton-driven nucleosynthesis theory, which places a spotlight on leptons, specifically electrons and their even more ghostly cousins, neutrinos. In the Standard Model, these particles are often seen as supporting actors, but this theory suggests they may have been directors of the cosmic play, subtly influencing the script of creation from the shadows. To understand their potential impact, we need to appreciate the incredible density of the early cosmos. For every single proton or neutron, there were over 1 billion neutrinos zipping through every cubic inch of space, barely interacting with anything, yet present in unimaginable numbers. Their primary role in the standard narrative is to mediate the balance between protons and neutrons through a process called weak interaction. Essentially, a neutron can turn into a proton by emitting an electron and an antineutrino, and a proton can turn into a neutron by absorbing an electron and emitting a neutrino. This delicate dance of transformation was constant until the universe cooled enough for these reactions to slow down, freezing the neutron-to-proton ratio. This ratio is the single most important number for nucleosynthesis, as it directly dictates how much raw material is available to build helium nuclei. The lepton-driven theory proposes that this process was far from simple and uniform. If there were even slight asymmetries or variations in the number or energy of these neutrinos, perhaps from the decay of other exotic particles or from the physics of the quark-gluon plasma transition, it could have created a situation where certain regions of the universe had a significantly higher density of these ghostly particles. In a region flooded with a high concentration of neutrinos, the weak interaction reactions would have been supercharged. This could have massively accelerated the conversion of neutrons into protons, or vice versa, dramatically altering the local neutron-proton ratio just before nucleosynthesis began. A pocket of the universe with more neutrinos might have ended up with far fewer neutrons, leaving it hydrogen-rich and helium-poor. Another region might have had its neutrons preserved, creating a helium factory. When everything averaged out, the final cosmic abundances we measure could be the blended result of these wildly different local environments shaped by the flow of neutrinos. But their influence might not stop there. Some highly speculative models suggest that neutrinos themselves could have catalyzed entirely new nuclear reaction pathways. In the incredible heat and density, a neutrino interacting with a neutron could theoretically facilitate the formation of a rare isotope or help a nucleus bypass an energy barrier that would normally halt a reaction. While such processes are exceedingly rare, in a universe with 1 billion neutrinos for every nucleon, even the most improbable event could happen enough times to leave a measurable mark on the elemental fingerprint. This theory challenges the proton-centric view of the early universe, painting a picture where the most abundant and least interactive particles in existence were silently pulling the strings, their ghostly fingerprints forever etched into the very first atoms. Now we venture into the realm of some of the most elegant and sought-after physics beyond the standard model with our 8th theory, supersymmetry. This isn't just a minor tweak to our understanding. It's a grand theoretical framework that proposes a profound and beautiful symmetry in nature, suggesting that every known fundamental particle has a hidden superpartner twin. While experiments have yet to definitively find these supersymmetric particles or sparticles, their potential existence opens a thrilling window into how the earliest universe might have operated, directly impacting the story of the first light elements. To understand their potential influence, imagine the early universe not just as a soup of quarks and electrons, but as a much richer and more diverse particle zoo. For every familiar quark, there would have been a hypothetical squark, for every electron a selectron, for every photon a photino. According to the theory, these superpartners would have been incredibly massive and unstable, decaying almost instantly in our current cold universe. But in the unimaginable energy of the first moments after the Big Bang, they would have been abundant and active participants in the cosmic drama. Their sheer presence would have altered the thermodynamics of the early cosmos, affecting how it expanded and cooled. More importantly, many of these particles would have interacted with ordinary matter through the weak nuclear force and gravity, providing new pathways for particles to transform and energy to be exchanged. One of the most significant ways supersymmetry could have left a mark is through the lithium problem. In the standard model, the amount of lithium-7 produced is highly sensitive to the density of neutrons available during nucleosynthesis. Certain supersymmetric particles, like the neutrino, a leading candidate for dark matter, could have directly influenced this balance. If these particles were present, they might have decayed or annihilated with each other right around the time nucleosynthesis was beginning. This process would have released a burst of energy, primarily in the form of high-energy photons and other particles. These photons could have had enough energy to blast apart the delicate deuterium nuclei that were just starting to form. Since deuterium is a crucial stepping stone to forming both helium and lithium, a reduction in its abundance would create a bottleneck, slowing down the entire chain of nuclear reactions and potentially leading to a lower final yield of lithium-7, bringing the theoretical prediction much closer to what we actually observe in ancient stars. Beyond solving the lithium puzzle, supersymmetry offers a breathtakingly direct connection between the formation of the first elements and the nature of dark matter itself. If the lightest supersymmetric particle is stable, as the theory predicts, it would not have decayed away. Trillions of these particles would have been forged in the early universe, and they would be with us today, forming the invisible halo of dark matter that surrounds our galaxy. This means the same physical process that potentially tweaked the abundances of lithium and helium also automatically produced the universe's missing mass. The atoms that make up our bodies and our world are, in this view, inextricably linked to the vast, unseen dark matter ocean we float in. The first elements become a fossil record not just of visible matter, but of the entire particle content of the infant cosmos. While the hunt for direct evidence of supersymmetry continues in particle colliders and deep underground labs, The ancient pattern of hydrogen, helium, and lithium in the oldest stars might just be whispering the first clues that this majestic symmetry is indeed a law of nature. To truly appreciate the cosmic significance of the first elements, we must confront one of the greatest mysteries in all of physics. Why does anything exist at all? According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. When a particle of matter meets its antimatter counterpart, they annihilate each other in a flash of pure energy. If the universe had begun with perfect symmetry, all of its contents should have mutually annihilated, leaving behind a cosmos filled with nothing but light. The simple, breathtaking fact that we are here, made of matter, in a universe full of stars and galaxies, is proof that this symmetry was broken. Something tipped the scales. This monumental event is called baryogenesis, and the baryogenesis connection theory proposes that the same physics that saved the universe from total annihilation also directly orchestrated the formation of the very first elements. The connection is not just philosophical, it's deeply practical. The number of protons and neutrons that survived that great annihilation is the single most important variable in the equation of Big Bang nucleosynthesis. This number, the baryon density, essentially sets the stage and writes the guest list for the entire process. It determines how many particles are available to collide, how frequently those collisions happen, and ultimately, how much of each element can be forged. In the Standard model, this density is taken as a given, a number we plug in based on what we observe. But the baryogenesis connection theory asks a more profound question. What if the way in which matter won out over antimatter left a specific, identifiable fingerprint on that baryon density, a fingerprint we can still read in the pattern of hydrogen, helium, and lithium today? Different theoretical models for how baryogenesis occurred predict different outcomes for the early particle soup. For instance, some models involve hypothetical super-heavy particles decaying asymmetrically, favoring the production of matter over antimatter. The specifics of those decays, the energy released, the types of particles created, and the timing of it all could have injected extra energy or even additional protons and neutrons into the cosmos right before or during nucleosynthesis. This wouldn't have been a gentle addition, it would have been a dramatic upheaval. A sudden influx of energy could have reheated certain regions of the universe, temporarily halting fusion or even breaking apart nuclei that had already formed. Alternatively, a model that produced matter unevenly, creating pockets with slightly more baryons than others, would lead to a scenario much like the inhomogeneous Big Bang, where nucleosynthesis proceeded at different rates and produced different yields depending on your location. The most tantalizing aspect of this idea is that it turns the first elements into a cosmic detective story. The specific abundances we measure are not just a random outcome, they could be a detailed logbook of the baryogenesis process itself. The precise ratio of deuterium to helium is exquisitely sensitive to the baryon density. The stubborn lithium problem could be a clue that the process wasn't perfectly smooth, hinting at the violent, particle decay-driven mechanism that first populated the universe with matter. By studying these elemental fossils with greater and greater precision, cosmologists aren't just learning about the first 3 minutes, they are indirectly testing theories about the first fractions of a second, probing the physics that made our very existence possible. The hydrogen in water, the helium in a birthday balloon, and the lithium in a battery may be the enduring legacy of the universe's most important and lopsided battle, a permanent record of the moment matter won its fragile victory over nothingness. To understand this, we first have to confront the greatest unsolved problem in theoretical physics, the clash between the two titans of 20th century science. On one side, we have quantum mechanics, which describes the bizarre and probabilistic world of the atom with incredible precision. On the other, we have Einstein's general relativity, which paints a beautiful picture of gravity as the curvature of spacetime by mass and energy. Individually, they are masterpieces, but together they are incompatible. This schism only becomes a crisis in the most extreme environments, like the center of a black hole, or the very first moment of the Big Bang, where densities and energies were so high that the quantum nature of spacetime itself must have been visible. This is the domain of quantum gravity, a theory we do not yet have, but whose potential effects we can try to imagine. One of the most captivating ideas from this speculative frontier is the concept of spacetime foam. Picture the smooth, continuous fabric of space we take for granted. Now, imagine zooming into a scale a billion times smaller than an atomic nucleus. At this level, the vacuum of space might not be smooth and silent at all. Instead, it could be a chaotic, seething, and turbulent foam, with tiny wormholes popping in and out of existence, and miniature black holes forming and evaporating in an instant. This isn't empty space, it's a frenzy of topological activity at the Planck scale. In the first moments of the universe, when all of reality was compressed into such a minuscule volume, this quantum foam wouldn't have been a hidden underlying layer. It was the entire structure of the cosmos. Now bring nuclear physics into this frenetic environment. The processes of Big Bang nucleosynthesis rely on something called nuclear cross-sections. This is essentially a measure of the probability that two particles will collide and stick together to form a new nucleus. These cross-sections are treated as fixed numbers, calculated and verified in our calm, modern-day particle accelerators where spacetime is flat and stable. But what if those probabilities were not fixed in the infant universe? In a spacetime foam, the very definition of a straight line or a short distance becomes meaningless. The path a proton takes to meet a neutron could be drastically warped or shortened by a temporary wormhole. A fleeting microscopic black hole could gravitationally focus a stream of particles, increasing their chance of collision in a specific spot. In this view, the nuclear cross-sections weren't constants. They were dynamic variables fluctuating wildly along with the quantum foam itself. This means the fusion rates for deuterium, helium, and lithium could have been significantly different, perhaps faster or more efficient, than our standard models assume. The possibilities get even stranger. Some theories suggest that this extreme quantum environment could have allowed for the temporary existence of exotic nuclear species that are utterly impossible in our current stable universe. Imagine a nucleus where the quarks within protons and neutrons are not so tightly confined, leading to a sort of smeared out or extended nuclear matter. Or consider the potential for reactions that don't just fuse particles, but involve the spacetime foam itself as a participant. Could a microscopic wormhole have acted as a bridge, allowing two particles to tunnel through to each other and fuse in a way that bypassed the normal energy barriers? While this sounds like science fiction, it is precisely the kind of effect a theory of quantum gravity might predict for such an extreme epoch. The existence of even short-lived exotic nuclei would have opened up entirely new reaction pathways for nucleosynthesis, creating and destroying elements through channels we cannot possibly replicate or study in any laboratory on Earth. The challenge, and the reason this remains one of the most speculative theories, is that we have no experimental data from that time. We are trying to use the fossil record of the light elements to reverse engineer the physics of a domain we do not understand. The abundances of hydrogen, helium, and lithium are our only clues. If a future, complete theory of quantum gravity, like string theory or loop quantum gravity, predicts a specific deviation from the standard model's nuclear cross-sections, and that deviation just so happens to solve the lithium problem perfectly, it would be a monumental breakthrough. It would mean that the first atoms carry within them an imprint not just of the first few minutes, but of the very first instances of time, when the universe was so small that the rules of reality were being written anew. But if the cosmic constants we depend on are, in fact, variable, it forces us to ask an even more profound question. What if our universe's specific settings aren't the only possible configuration? This brings us to an idea that stretches the boundaries of cosmology itself, the multiverse imprint theory. This concept suggests that the precise mix of hydrogen, helium, and lithium we observe might not be a unique, inevitable outcome of our universe's laws, but rather a single data point in a vast cosmic landscape, a fingerprint left by a much larger multiversal structure. To grasp this, imagine our universe's fundamental constants: the strength of gravity, the mass of an electron, the strength of the nuclear forces, as the dials on a vast control board. In our reality, these dials are set to very specific values that allow for the existence of atoms, stars, planets, and life. Tweak any one of them even slightly, and the entire cosmic experiment fails. Atoms might not form, or stars could never ignite. The astounding fact that these constants appear so perfectly fine-tuned for our existence is one of the deepest mysteries in science. The multiverse theory offers a breathtaking explanation. Perhaps there isn't just one universe, but a near-infinite number of them, each with its own random settings on that cosmic control board. Most of these universes would be stillborn or barren, their physical laws incapable of producing any complex structure. But in a rare few, like our own, the dials happen to land in the perfect sweet spot for creation. So where do the first light elements fit into this? They are the first and most fundamental test of those settings. The process of Big Bang nucleosynthesis is exquisitely sensitive to the values of those constants. For example, if the strength of the strong nuclear force were just a few percent stronger or weaker, it would drastically alter the stability of deuterium. Too strong, and nearly all the hydrogen would have fused into helium and beyond, leaving no long-lived stars to power planets. Too weak, and deuterium would never form at all, preventing the chain of fusion that builds helium and lithium, leaving the universe a boring expanse of pure hydrogen. The fact that we live in a universe where deuterium is stable enough to act as a stepping stone, but not so stable that it halts all progress, is a remarkable coincidence. Proponents of the multiverse imprint theory argue that this is no coincidence at all. They propose that we only find ourselves in a universe where the elemental abundances are life-friendly because that's the only kind of universe we can observe. The specific ratios we measure, the exact 75% hydrogen, 25% helium, and tiny lithium fraction, could be a signature that our universe's particular dial settings fall within the narrow habitable range. In this view, the light elements are a kind of cosmic barcode. By scanning it, we might be able to infer the existence of other universes with different barcodes, even if we can never directly visit them. If a future, complete theory of the multiverse predicts that habitable universes must have a helium abundance between 20 and 25%, for instance, then our observation of 25% becomes powerful supporting evidence. This idea transforms a potential anomaly like the lithium problem from a puzzle to be solved into a potential feature to be understood. Perhaps the lithium discrepancy isn't a sign that our model of nucleosynthesis is wrong, but that it's uniquely right for our specific universe within the multiverse. The abundance we see might be the precise value that emerges from one particular, life-allowing combination of physical laws, different from the average value across the entire multiverse. It's a humbling and awe-inspiring proposition. The atoms forged in the first 3 minutes become a message in a bottle, telling us not only about our own origins, but hinting at the existence of a reality so vast and strange that our entire cosmos is just one leaf on an infinite tree. Yet for all its pervasive gravitational influence, dark matter is famously aloof, refusing to interact with ordinary matter through anything but gravity. But what if that wasn't always the case? Our 12th theory, the dark matter interaction theory, dares to imagine a more sociable early universe where dark matter didn't just warp the gravitational landscape but actively mingled with the primordial soup, leaving a permanent signature in the recipe for the first elements. To understand how this could work, we need to think of dark matter not as a single monolithic substance, but as a family of potential particles, each with its own unique properties. While most models assume these particles are collisionless, simply passing through ordinary matter like ghosts, some compelling theoretical candidates could have been far more interactive in the extreme heat and density of the early cosmos. One such candidate is the theoretical SIMP, or strongly interacting massive particle. As the name implies, these particles wouldn't be shy. They would frequently bump into and scatter off protons and neutrons, much like one billiard ball hitting another. In the first few minutes, this would have had a dramatic and direct effect on the process of nucleosynthesis. This constant jostling would have served as a powerful source of friction, effectively transferring energy between the dark matter and the primordial plasma. In some models, this interaction acts like a cosmic brake, slowing down the overall expansion rate of the universe during those crucial first minutes. A slower expansion gives particles more time to find each other and fuse, potentially allowing for the production of more helium-4, which could help align certain theoretical predictions with observations. In other scenarios, the energy transferred from the dark matter could have locally heated the plasma, creating tiny hotspots where nuclear reactions proceeded at a slightly accelerated pace, or conversely, cooling other regions where interactions were less frequent. But the influence might go even deeper than just altering the environment. Some highly speculative models propose that certain types of dark matter particles could have participated directly in the nuclear reactions themselves. Imagine a dark matter particle being captured by a newly forming helium nucleus, temporarily creating a bizarre, hybrid, dark nucleus. The presence of this extra particle could stabilize the nucleus in a way that changes its probability of interacting with other particles, either opening up new fusion pathways or effectively shutting down existing ones. If such processes occurred even rarely, their cumulative effect across the entire universe could have subtly shifted the final abundances of the light elements, particularly that persistent lithium problem. The key idea here is that dark matter wasn't just a passive spectator providing the gravitational scaffolding for galaxies to form later. It might have been an active, hands-on chef in the kitchen, directly tweaking the ingredients of the cosmic soup as it was being prepared. The allure of this theory is that it offers a potential two-for-one solution to major cosmological puzzles. The same dark matter particle that explains the missing mass of the universe, the reason galaxies spin the way they do and light bends around clusters, could also be the key that unlocks the mystery of the first elements. This creates a beautiful, interconnected story where the visible and the invisible realms of the cosmos are not separate but were deeply entwined from the very beginning. While evidence for such strong interactions remains elusive, the fact that the light element abundances provide a testable window into the possible nature of dark matter is a powerful reminder that the universe's earliest moments hold clues to its deepest, darkest secrets. Now consider a force so fundamental it guides compass needles and shapes entire galaxies, a force that might have been present at the very dawn of time itself. We're talking about magnetism, and our 13th theory proposes that powerful primordial magnetic fields were woven into the fabric of the infant cosmos, actively guiding the formation of the first elements in ways we are only beginning to understand. In the standard model of Big Bang nucleosynthesis, the early universe is often pictured as an electrically neutral soup, where the only dominant forces are gravity and the nuclear interactions. But what if that picture is incomplete? What if space was already laced with vast, invisible threads of magnetic force from the very beginning? The origin of these hypothesized fields is a mystery in itself. They could be a relic from a phase transition in the early universe, perhaps when the electromagnetic and weak nuclear forces split into two distinct entities. Alternatively, they might have been generated by the turbulent motions of that incredibly dense plasma, acting like a cosmic dynamo in the first fractions of a second. However they arose, their potential influence is profound. A strong, large-scale magnetic field does not just gently push particles around. It forces charged particles like protons to travel in tight, spiraling paths along the field lines rather than zipping off in random directions. This organized motion could have drastically altered the nuclear physics of the early universe. In a strong magnetic environment, particles are effectively funneled, their motions correlated along the direction of the field. This means that when two protons approach each other, they aren't just colliding randomly. Their trajectories are being guided by this invisible cosmic architecture. This guidance could significantly increase the probability of a successful collision and fusion, essentially turning the magnetic field lines into particle accelerators that enhance the rates of key reactions. For instance, the formation of deuterium, the crucial first step towards building helium, might have happened more efficiently in regions where these fields were strongest, leading to local overproductions of heavier elements. But the impact might be even more exotic than simply speeding things up. Some theoretical work suggests that a powerful magnetic field could actually modify the quantum mechanical properties of the particles themselves, slightly altering the fundamental nuclear cross-sections that dictate how likely fusion is to occur. It's as if the magnetic field subtly rewrites the rules of engagement for the nuclear reactions, potentially allowing for the creation of minuscule amounts of elements like beryllium or boron that are otherwise impossible to account for in the standard model. Furthermore, these fields could have created a universe with a distinct directional preference or anisotropy. Instead of a perfectly uniform distribution of elements, there might have been vast, light-year-wide regions that were slightly richer in helium, while others remained dominated by hydrogen, their elemental makeup dictated by the orientation and strength of the local magnetic landscape. The tantalizing possibility is that the imprint of these fields might still be observable today. If they existed, they would have left fossilized remnants, incredibly weakened by the universe's expansion but still present. Astronomers are actively searching for these ancient magnetic fingerprints in the subtle polarization patterns of the cosmic microwave background and in the alignment of light from the most distant quasars. Finding conclusive evidence would not only confirm a dramatic new player in the story of nucleosynthesis, but would also provide a direct link between the forces that guided the formation of the first atoms and the magnetic fields that now permeate galaxies, including our own Milky Way. It suggests that the same fundamental force that organizes galaxies today may have also been a master architect at the very birth of the elements. While the previous theories have focused on particles influencing nucleosynthesis through collisions or decays, our next idea explores a far more subtle and ghostly transformation happening in the background, one that could have delicately tweaked the most important number in the entire process. This is the neutrino oscillation impact theory, and it centers on one of the most bizarre quantum behaviors in the particle zoo, the ability of neutrinos to spontaneously change their identity. We've already seen how crucial the initial neutron-to-proton ratio was for determining the final amounts of hydrogen and helium. That ratio was largely set by the weak interaction reactions, where a neutron turns into a proton or vice versa, mediated by a constant flood of electrons and neutrinos. In the standard model, this process is assumed to happen with a certain predictable efficiency. But what if the neutrinos themselves were undergoing a fundamental change during this very period? We now know from experiments that neutrinos are not static. They oscillate between their three different flavors: electron, muon, and tau. An electron neutrino emitted in a reaction can, as it travels through space, morph into a muon or tau neutrino before interacting with something else. This isn't a minor detail, it's a core part of their quantum nature. In the incredibly dense environment of the early universe, this oscillation behavior could have been dramatically amplified. The presence of such a dense sea of electrons, neutrinos, and other particles creates a complex environment that can either enhance or suppress these oscillations through a phenomenon known as matter-enhanced oscillation, or the Mikhaev-Smirnov-Wolfenstein effect. Essentially, the dense electron background makes it more or less favorable for an electron neutrino to maintain its identity or to flip into another flavor. This isn't just a theoretical curiosity, it would have had direct and measurable consequences. The weak interaction reactions that set the neutron-proton freeze-out ratio depend specifically on the electron neutrino and antineutrino. Their abundance and energy spectrum are the key drivers. If oscillations were significantly altering the number of electron neutrinos present at the precise moment these reactions were slowing down, it would have directly changed the outcome. For example, if matter-enhanced oscillations caused a larger fraction of electron neutrinos to convert into muon or tau neutrinos, it would have effectively depleted the pool of particles available to convert neutrons back into protons. This would have left the universe with a higher fraction of neutrons just before nucleosynthesis began, leading to the production of more helium-4. Conversely, if the oscillations worked in the opposite way, preserving or even increasing the number of electron neutrinos, it could have accelerated the conversion of neutrons into protons, resulting in a hydrogen-richer, helium-poorer cosmos. The precise details depend on the still unknown absolute masses of neutrinos and their hierarchy, meaning the fossil record of the light elements could be our oldest data point in the quest to understand these elusive particles. The calculations involved are incredibly complex, weaving together quantum mechanics, thermodynamics, and nuclear physics. Different models of neutrino physics, such as whether their masses are normally ordered or inverted, predict subtly different outcomes for the primordial element abundances. This means that by measuring the exact ratios of hydrogen, helium, and lithium in the oldest stars with ever-increasing precision, cosmologists are indirectly testing fundamental properties of neutrinos that are exceedingly difficult to measure in laboratories on Earth. A confirmed discrepancy that aligns with a specific oscillation scenario would be monumental. It would prove that these ghostly particles, famous for barely interacting, didn't just witness the birth of the elements their quantum-scale identity crisis actively helped write the recipe. For centuries, we've understood our universe to have 3 dimensions of space and 1 of time, a 4-dimensional stage upon which all of physics plays out. But what if that stage was much, much bigger in its earliest moments? This brings us to a theory that draws from one of the most ambitious ideas in modern physics, string theory. The extra dimensions influence theory proposes that our familiar 4-dimensional reality was not the full story in the universe's first instance. Instead, there may have been additional, hidden spatial dimensions curled up so tiny that we cannot perceive them today. In the incredible energy and density of the Big Bang, these extra dimensions could have been unfurled, playing an active and dramatic role in the physics that govern the creation of the first elements. To visualize this, imagine a garden hose stretching across a lawn. From a distance, it appears to be a simple one-dimensional line, but if you were an ant crawling on its surface, you would discover a second dimension, the circular direction going around the hose's circumference. String theory suggests that our universe might be similar. While we perceive 3 large spatial dimensions, there could be 6 or 7 additional dimensions curled up into a space so minuscule that even a single atom would be gargantuan in comparison. In the everyday, low-energy world we inhabit, these dimensions are completely hidden. But rewind to the first fraction of a second after the Big Bang, when the universe was unimaginably hot and dense, and the story changes entirely. At those energy scales, the distinction between large and small dimensions blurs. Those tightly curled dimensions could have temporarily unfurled, making the universe effectively 10 or 11-dimensional for a fleeting moment. This shift in the very dimensionality of spacetime would have had a profound impact on the fundamental forces, particularly gravity. In our four-dimensional world, gravity follows the familiar inverse square law. Its strength diminishes with the square of the distance. But in a universe with more spatial dimensions, gravity would behave differently. Its strength would diminish much more rapidly. If extra dimensions were open for business during the era of nucleosynthesis, the force of gravity would have been exponentially stronger at very small scales. This isn't a minor adjustment, it's a complete overhaul of the engine driving the universe's expansion. A stronger gravitational pull in those first moments would have caused the cosmos to expand and cool at a radically different rate, directly altering the timeline and efficiency of nuclear fusion. That critical 3-minute window for building elements might have been significantly shorter or longer, changing the final abundances of hydrogen, helium, and lithium in ways the standard 3-dimensional model could never predict. Beyond just tweaking gravity, these extra dimensions could have introduced an entirely new cast of particle characters into the nuclear drama. In string theory, the different ways a string vibrates in these multi-dimensional spaces correspond to different particles and forces. With more dimensions available, a whole new spectrum of exotic, high-mass particle species could have briefly existed. These particles, known collectively as Kaluza-Klein modes, would have been too massive to exist in our current cold universe, but in the high-energy forge of the Big Bang, they would have been abundant. Crucially, many of these particles could have interacted through the strong and weak nuclear forces. Imagine a heavy, higher-dimensional particle participating in a fusion reaction between a proton and a neutron, acting as a short-lived catalyst that allows them to bind together more easily. Or consider the possibility of entirely new nuclear reaction pathways opening up, channels that are simply forbidden in a 3-dimensional universe, potentially allowing for the creation of trace amounts of elements like beryllium that the standard model cannot account for. The echoes of this multi-dimensional beginning might be frozen into the elemental fossil record we observe today. The persistent lithium problem, for instance, could be a direct signature of these extra dimensions. If their presence altered the expansion rate of the universe at just the right moment, it could have changed the density of neutrons available, neatly resolving the discrepancy between prediction and observation. The appeal of this theory is its breathtaking scope. It suggests that the recipe for the atoms that make up our world was written not in 3 dimensions but in 10. While still highly speculative and far from proven, the extra dimensions influence theory represents a thrilling frontier. It challenges us to consider that the deepest secrets of the cosmos are not just hidden in the past, but are encoded in the very shape of reality itself, a shape that may have been far more complex and beautiful in the brilliant flash of the beginning. These phase transitions weren't merely a change in temperature. They were dramatic, fundamental reorganizations of the cosmos, moments when the very laws of physics as we know them snapped into focus. To understand their potential impact, we need to picture the universe not as a smoothly evolving soup, but as a pot of water coming to a rolling boil. The electroweak transition, for instance, occurred when the universe was just a picosecond old. At energies above this transition, the electromagnetic force and the weak nuclear force were unified into a single, symmetric electroweak force. As the cosmos cooled below a critical temperature, this symmetry was spontaneously broken, much like liquid water freezing into structured ice crystals. This momentous event gave masses to particles like the W and Z bosons and the Higgs boson itself, fundamentally altering how particles interacted. Now, imagine this transition not happening uniformly everywhere at once, but through the formation and expansion of bubbles. In a cosmological first-order phase transition, tiny bubbles of the new, lower-energy, true vacuum would randomly nucleate in the sea of the old, high-energy, false vacuum. These bubbles would then expand at nearly the speed of light, eventually colliding and merging until the entire universe had converted. It's within the violent dynamics of these colliding bubble walls that the conditions for truly exotic physics emerge. The walls themselves would be regions of incredible energy density, potentially creating shock waves and temperatures far higher than the surrounding plasma. If nucleosynthesis was underway or about to begin when this transition occurred, these bubble walls would have sliced through the cosmos, creating a patchwork of regions with wildly different thermodynamic histories. Within these bubbles of true vacuum, the rules of the game had literally changed. The particle masses and interaction strengths were now set to their modern values. But in the regions between bubbles, particularly in the crashing fronts of colliding walls, the energy released could have been so immense that it temporarily reverted space back to a higher energy state, a fleeting resurrection of the symmetric false vacuum. This creates a stunning possibility, a universe that is not a single, coherent entity, but a chaotic mosaic of different physical domains, each with its own slightly different settings for key constants during those critical first minutes. In one region, the neutron-proton mass difference might have been minutely altered, changing the freeze-out ratio. In another, the strength of the strong nuclear force could have been perturbed, making it easier or harder for deuterium to form. This means the process of building the first nuclei wouldn't have been a single, universal event, but a collection of many different events happening in different pockets of space, each with its own unique yield of hydrogen, helium, and lithium. The quantum chromodynamic phase transition presents an even more direct and dramatic scenario. This is the moment when the free-roaming quarks and gluons of the quark-gluon plasma became confined into protons and neutrons. If this transition was first order occurring through bubble nucleation, it would have been a fantastically violent process. The latent heat released as these bubbles of confined nuclear matter expanded and collided would have generated intense shock waves that reverberated through the primordial plasma. These shocks could have acted like cosmic pressure cookers, creating localized regions of extreme density and temperature perfectly tailored for nuclear fusion. It's conceivable that in these intense shock fronts, the fusion of elements didn't just follow the standard pathway. It might have leaped ahead, bypassing the usual bottleneck of deuterium to forge elements like lithium, beryllium, or even boron directly from the quark-gluon plasma itself in a process known as quark-nova nucleosynthesis. The enduring mystery is how any signature of this primordial patchwork could have survived. Wouldn't these different domains have simply mixed and averaged out into a uniform blend as the universe continued to expand? Perhaps not entirely. If the phase transitions completed quickly enough, the different elemental yields in these vast bubbles, each potentially larger than our observable universe today, would have been frozen in, preserved like fossils in separate cosmic strata. When we look out into the deepest space, measuring the abundances of light elements in incredibly ancient gas clouds, we might actually be sampling one of these individual bubbles. The slight variations we see from one region to another might not be measurement errors. They could be the faint, billion-year-old echo of a time when the universe itself was crystallizing from a formless frenzy of energy into the structured reality we know, its final elemental makeup determined by the chaotic collage of its own birth. Now, let's shift our perspective from the strange quantum realm to the realm of raw, chaotic motion. Up to this point, we've largely considered the early universe as a relatively smooth, if incredibly hot, fluid. But what if it was born in a state of incredible, violent turbulence? The primordial turbulence theory proposes exactly that, suggesting the infant cosmos was a churning, roaring sea of plasma, and that this chaotic motion itself played a direct and creative role in shaping the first elements. To truly grasp this idea, picture the most powerful thunderstorm you can imagine, multiplied by a factor of billions. Now, instead of air and water, the entire universe is the storm, a dense, seething plasma of fundamental particles. This isn't a gentle simmer, it's a frenzy of whirlpools, jets, and shock waves moving at relativistic speeds. Where did this turbulence come from? The seeds were likely planted in the first instance by the same quantum fluctuations that eventually grew into galaxies. As the universe expanded, these microscopic ripples could have been amplified into massive currents and eddies within the primordial soup, a chaotic dance set in motion at the very beginning. This turbulence would have done two critical things. First, it would have acted as a cosmic blender. Even if the initial conditions for nucleosynthesis were slightly uneven, perhaps due to the influences we've already discussed, like variable constants or inhomogeneous phase transitions, turbulence would have vigorously mixed these different regions together. A pocket of plasma that had produced a little extra helium might have been swirled into a region that was mostly hydrogen, averaging out the final composition in a way that could account for the subtle discrepancies we see. But the second, and perhaps more potent, effect is the creation of shock waves. When these massive flows of plasma collided, they would have generated tremendous shock fronts, cosmic sonic booms of unimaginable power. Within these shock waves, conditions would have been far more extreme than in the calm plasma outside. The density and temperature would have spiked dramatically. It's within these fleeting, intense hotspots that the magic could have happened. The standard model of nucleosynthesis relies on a fairly steady decline in temperature and density. But a shock wave provides a sudden, violent reheating and recompression of the material. For a brief moment in these localized crucibles, the clock on nucleosynthesis could have been turned back. The temperature might have surged high enough to restart fusion reactions that had already halted in the surrounding, cooler plasma. Protons and neutrons that had been drifting too far apart to interact could have been slammed back together with incredible force. This could have allowed for an extra, late-stage burst of element formation, potentially creating a small overabundance of certain isotopes or even permitting the fleeting creation of elements slightly heavier than lithium, like beryllium or boron, which the standard model cannot produce. The universe wouldn't have just forged its elements in a steady oven. It would have finished them with a series of intense, scattered blowtorches. The beauty of this theory is that it offers a dynamic and physical solution to the problem of uniformity. It doesn't require new particles or altered laws of physics, just the recognition that the early universe was likely a far more violent and chaotic place than our smoothest models often assume. The faint variations in elemental abundances we detect across the cosmos might not be measurement errors or signs of unknown physics, but could instead be the lasting imprint of this primordial storm, the final eddies of a turbulence that shaped reality from its very first seconds. Consider for a moment the electron in your body, a particle so small and yet so fundamental to the structure of every atom that makes you who you are. Its mass is a number we take for granted, a constant etched into the bedrock of physics. But what if that number wasn't always the same? Our 18th theory, the time-varying fundamental mass theory, dares to ask this profound question, proposing that the very building blocks of matter might have had different weights in the universe's explosive first moments, a shift that would have completely rewritten the recipe for the first light elements. To understand how a change in mass could have such a dramatic effect, we need to look at the delicate nuclear physics at play during Big Bang nucleosynthesis. The entire process is a breathtakingly precise chain reaction, and one of its most critical steps is the formation of deuterium, the heavy isotope of hydrogen. A single proton and a neutron must come together and bind, but they are held apart by their mutual electrical repulsion. They can only overcome this barrier and fuse if they collide with enough energy. The probability of this happening is exquisitely sensitive to the mass of the electron. Why? Because the energy levels within the newly formed deuterium nucleus and the way it interacts with high-energy photons are dictated by quantum mechanics and depend directly on the electron's mass. A different electron mass would mean a different probability for this crucial first step to occur, either creating a bottleneck that halts the entire process or opening the floodgates to overproduction. But the potential influence goes far deeper than just deuterium. The stability of every nucleus that forms after it, helium, lithium, beryllium, is governed by its binding energy, the nuclear glue that holds it together. This binding energy isn't an arbitrary number. It emerges from the complex interplay between the strong nuclear force and the electromagnetic forces within the nucleus, all of which are fundamentally tied to the masses of the constituent particles. If the electron mass were even a fraction of a percent different in the early universe, it would have subtly altered the balance of these forces for every single nucleus. A lithium nucleus, for instance, might have become slightly less stable, making it more prone to being broken apart by a high-energy photon before it could accumulate. Conversely, a helium nucleus might have become even more tightly bound, sucking up more of the available neutrons and leaving less hydrogen behind. The final cosmic abundances we observe are a frozen record of these nuclear stability values, and a time-varying mass offers a direct mechanism to tweak them into alignment with what we actually see in the oldest stars. The appeal of this radical idea is that it provides a single, elegant lever to pull that could adjust multiple outcomes at once, potentially solving several small puzzles like the lithium problem with one grand conceptual shift. The challenge, of course, is monumental. The masses of fundamental particles are cornerstones of the standard model of physics, and the idea that they could change over time strikes at the heart of our understanding of the laws of nature. Proponents of the theory suggest that such variation could be linked to the changing value of other fundamental fields as the universe expanded and cooled, particularly the Higgs field, which is responsible for granting mass to particles in the first place. If the Higgs field itself had not yet settled into its modern minimum value, the masses it bestowed could have been in a state of flux. Critics rightly point out that there is no direct evidence for such variation, and that any significant change would likely have caused catastrophic instability, preventing the universe from evolving into the structured cosmos we inhabit. Yet the theory remains a captivating frontier of thought, reminding us that the constants we hold sacred might be the greatest variables of all, and that the first atoms may carry within them the secret history of mass itself. But what if the story of the elements doesn't begin with a bang at all? To venture even further back, we must consider the possibility that our universe was not the absolute beginning, but merely a new chapter in a much grander cosmic cycle. This brings us to our 19th theory, the pre-Big Bang scenarios theory, which dares to ask what might have come before the singularity and how its echoes could have orchestrated the elemental symphony we observe today. The Standard Big Bang model describes the universe emerging from a state of infinite density and temperature, a point where our known laws of physics simply break down. Pre-Big Bang theories attempt to peer beyond this veil, proposing a variety of mechanisms through which our universe could have been born from a prior cosmological state. One of the most prominent ideas is the cyclic model, which envisions an eternal sequence of universes, each ending in a big crunch that gives rise to the next Big Bang in an endless cycle. Another compelling concept is the ekpyrotic universe, born from the collision of two higher dimensional branes in a bulk space, an event of unimaginable energy that we would perceive as our own Big Bang. In these models, our universe is not a singular creation event but a rebirth, a phoenix rising from the ashes of a previous cosmos. If our universe did indeed inherit something from a predecessor, how could that legacy be imprinted on the first light elements? The answer lies in the initial conditions. The process of Big Bang nucleosynthesis is exquisitely sensitive to its starting parameters, the exact temperature, density, and ratio of particles at the moment the fusion chain begins. In a cyclic model, the collapse of the previous universe wouldn't necessarily erase everything. Information about its final composition, its entropy, or the specific vibrations of its fundamental fields could be somehow preserved through the bounds. This means that when our universe exploded into existence, it didn't start with a blank slate. It may have begun with a specific, preset particle density or a particular distribution of energy that was a direct inheritance from its forebear. This inherited cosmic DNA would have immediately steered nucleosynthesis down a slightly different path, potentially resulting in elemental abundances that differ from the predictions of a universe born from nothing. The ekpyrotic scenario offers an even more direct mechanism. The violent collision of two brains would not only generate the heat and energy for a Big Bang, but could also produce a spectrum of primordial density fluctuations, the seeds for all future structure. The specific character of these fluctuations is determined by the physics of the brain collision itself. If that physics differed from the inflationary mechanism of the standard model, it would have created a different pattern of hot and cold spots in the early plasma. These variations would have acted as local catalysts or inhibitors for nuclear fusion during those first 3 minutes. Some regions, born from a particularly energetic part of the collision, might have been primed to overproduce helium. Others, quieter in their origin, might have remained hydrogen-rich. The average abundances we measure across the entire sky could therefore be a kind of fossilized echo of that primordial brain collision, a statistical signature of the event that gave our universe its start. The most profound implication of these pre-Big Bang theories is the possibility of encoded information. If a previous universe existed, its fundamental constants, its particle content, or even its history could have left a subtle imprint on the one physical record we have from the absolute beginning, the primordial element abundances. The precise ratio of deuterium to hydrogen or the stubborn lithium discrepancy might not be an error in our models but a message. It could be a cosmic signature, a fingerprint left by the laws of physics that governed a universe that came before our own, a set of rules that may have been subtly different from our own. Finding such a signature would be one of the most monumental discoveries in all of science, transforming our understanding of reality from a one-time event into an eternal, perhaps infinite, tapestry of cosmic cycles, with the recipe for the first atoms serving as our only link to the chapters that came before our own. This brings us to a theory that stands apart from all others, one that shifts the focus from how the elements formed to why we observe the specific values we do. It's called the anthropic principal selection theory, and it ventures into a realm that is both deeply scientific and profoundly philosophical. At its heart, this idea suggests that the primordial abundances of hydrogen, helium, and lithium might not be a random or even a uniquely determined outcome. Instead, they could be the only possible values that observers like us could ever measure because they are a prerequisite for our own existence. To grasp this, we need to consider the concept of fine-tuning. The process of Big Bang nucleosynthesis is exquisitely sensitive to the fundamental constants of the universe. The strength of the strong nuclear force, the mass of a neutron, the expansion rate of the cosmos tweak any of these dials even slightly, and the entire cosmic outcome changes dramatically. For instance, if the strong force were just a few % stronger, 2 protons could fuse together directly, bypassing the deuterium bottleneck entirely. This would cause nearly all the hydrogen in the universe to rapidly fuse into helium and then into heavier elements like carbon and oxygen. There would be no long-lived, stable hydrogen-burning stars like our Sun. Without such stars, there are no stable planetary systems, no steady sources of energy, and likely no planets like Earth where life could arise and evolve over billions of years. Conversely, if the strong force were slightly weaker, deuterium would be so unstable that it would never form at all. The entire chain of nuclear reactions would be stillborn, leaving a universe composed of nothing but boring, inert hydrogen gas, incapable of forming any complex chemistry whatsoever. The anthropic principle provides a startling framework for this observation. In its weak form, it simply states that the conditions we observe in the universe must be compatible with the existence of conscious life that is observing it. We shouldn't be surprised to find ourselves in a universe with the right elemental ingredients for life, because we couldn't possibly find ourselves in one that didn't have them. The light element abundances in this view are not a puzzle to be solved so much as a selection effect. We are here to measure a 75% hydrogen, 25% helium universe because that is one of the very few recipes that allows for stars, planets, and biologists. In countless other universes, perhaps within a vast multiverse, with different physical constants, nucleosynthesis produced wildly different results. Those universes remain dark, lifeless, and unobserved. Some researchers take this a step further, pointing to the specific value of the lithium-7 abundance and its apparent discrepancy. Could it be that the observed value, which seems like a problem for our models, is actually the optimal value for life? Perhaps a slightly higher lithium abundance would have catalyzed too much fusion in the first stars, causing them to burn out too quickly to nurture life-bearing planets. Or maybe a lower abundance would have hindered the specific chemical pathways needed for probiotic chemistry on rocky worlds. The stubborn lithium problem might not be an error in our physics, but a profound clue that we are looking at the universe from a very privileged and necessarily biased point of view. This theory doesn't replace the physical mechanisms of the other theories. Instead, it sits above them, offering a reason why one particular outcome out of a near-infinite set of possibilities is the one we call home. It suggests that the atoms we are made of were not just forged in a cosmic furnace, but were also pre-selected by the very fact of our existence, a truly humbling and awe-inspiring conclusion to our search for origins. Yet, even as we explore these grand ideas of cosmic cycles and existential selection, we must also consider the very framework that holds our universe together, gravity itself. For decades, Einstein's theory of general relativity has been the undisputed foundation of cosmology, describing how matter and energy curve space-time to create the force we know as gravity. It is this theory that underpins our entire standard model of Big Bang nucleosynthesis, governing the expansion rate of the early universe and setting the stage for all that followed. But what if our understanding of gravity is incomplete, especially under the extreme conditions of the cosmos's first moments? This leads us to the intriguing possibility of modified gravity theories and their potential impact on the creation of the first elements. The most prominent of these alternative ideas is known as modified Newtonian dynamics, or MUND. Originally proposed to explain the rotation curves of galaxies without invoking dark matter, MUND suggests that gravity behaves differently at very low accelerations than Newton or Einstein predicted. While MUND is primarily a model for galactic scales, its implications ripple all the way back to the beginning. If gravity's strength isn't constant across all scales and accelerations, then the expansion history of the universe would be different. During nucleosynthesis, the universe was expanding at an incredible rate, and the gravitational pull of all that dense matter and radiation was the primary brake on that expansion. A modified theory of gravity could mean that this braking effect was stronger or weaker than in the standard model. Imagine the universe's expansion as a cosmic hourglass, with the flow of sand representing the passage of time available for nuclear reactions. In the standard model, gravity sets the size of the neck of the hourglass, determining how quickly the sand flows. A modified gravity theory could either pinch that neck shut faster or open it wider. If gravity were effectively stronger in the early universe due to these modifications, it would have slowed the expansion more dramatically. This would have given protons and neutrons more time to find each other and fuse, potentially allowing for a much more efficient production of helium and even the creation of elements beyond lithium. Conversely, if a modified gravity model resulted in a weaker effective pull, the universe would have expanded even faster, cutting the nucleosynthesis window short and leaving us with a cosmos dominated by hydrogen, with even less helium and lithium than we see today. The precise elemental abundances we observe could be acting as a cosmic gauge, measuring the true behavior of gravity under conditions we can never replicate in a laboratory. But the potential for modification doesn't stop with MUND. Higher dimensional gravity theories, often arising from string theory, propose that gravity is inherently weaker than the other forces because it can leak into extra, hidden spatial dimensions. In the everyday world, these dimensions are curled up too small to notice. However, in the high-energy, high-density environment of the early universe, these extra dimensions might have been more significant. If gravity was able to seep into these other dimensions during the first few minutes, its apparent strength in our familiar 3 dimensions would have been reduced. This would have diminished gravity's role in slowing the expansion, causing the universe to blow apart even faster than in the standard model. A more rapid expansion means the particle soup would have thinned out more quickly, lowering the chances for successful collisions and stifling the production of heavier elements. The observed helium abundance acts as a very tight constraint on such models. Any theory that alters gravity must still deliver a universe that is 25% helium, not 0% or 100%. The true power of using nucleosynthesis to test these ideas is that it provides a clean, simple, and incredibly precise laboratory. The physics of nuclear fusion is well understood from particle accelerators and stellar models. The predictions of the standard cosmological model using standard gravity are very sharp. This means that any deviation in the predicted abundances of deuterium, helium, and lithium is a potential red flag, a sign that something in our model is amiss. That something could very well be our theory of gravity. While the evidence for dark matter and the stunning success of general relativity on large scales make a strong case for the standard model, the first light elements remain a tantalizing window into a possible alternative. They challenge us to consider that the force which shapes galaxies and bends light might have played by a slightly different set of rules when the universe was born, and that the recipe for the atoms all around us is the lasting signature of that forgotten law. Now let's journey into one of the most abstract yet deeply fascinating ideas on our list, a theory that takes us from the realm of nuclear physics straight into the heart of quantum mystery. This is the quantum decoherence effects theory, and it asks us to reconsider a fundamental assumption about the early universe, that it behaved classically from the very start. We're so used to thinking of particles as tiny billiard balls bouncing around, but in reality, at the most fundamental level, they exist as probability waves, fuzzy, spread-out entities that can be in multiple states at once, only settling into a definite reality when measured or observed. This bizarre quantum behavior is what allows particles to tunnel through barriers or interfere with themselves. But in our large, warm, noisy world, this quantum weirdness is constantly being washed away by a process called decoherence, where interactions with the environment force quantum systems to collapse into a single classical state. In the first few minutes of the universe, however, the environment was unlike anything we can imagine. It wasn't just hot and dense. It was a system where every particle was intimately connected to every other particle, a place where quantum correlations could have stretched across vast distances. The quantum decoherence effects theory proposes that this primordial soup might not have fully decohered. It might have retained its quantum coherence for a crucial period, meaning that the particles participating in the first nuclear reactions weren't behaving like classical objects at all. They were still entangled probability waves. How could this bizarre state of affairs have influenced the creation of the first elements? The answer lies in the very nature of nuclear reaction probabilities. The rates of fusion reactions that built deuterium, helium, and lithium are calculated using classical probabilities. We assume a proton has a definite position and momentum when it collides with a neutron. But if these particles were still in a coherent quantum state, their behavior would be governed by wave functions that can overlap and interfere. This means the probability of two particles fusing might not have been a fixed number. It could have been enhanced or suppressed by quantum interference effects. Imagine two protons approaching each other. In a classical world, they have a certain chance of tunneling through their mutual electrical repulsion to fuse. But in a coherent quantum universe, the wave functions of these protons could constructively interfere, making that tunneling event much more likely, or destructively interfere, making it virtually impossible. This isn't just a minor adjustment, it's a complete overhaul of the statistical mechanics underpinning nucleosynthesis. Entire reaction pathways could have been opened or closed based on these quantum correlations, potentially leading to a different final mix of elements than our classical models predict. The potential implications grow even stranger when we consider entanglement. It's possible that different nuclear species were quantum mechanically entangled with each other. This means the fate of a deuterium nucleus forming in one region could have been instantly linked to the state of a helium nucleus forming light years away, a connection that persists regardless of distance. This spooky action at a distance, as Einstein called it, could have created subtle correlations in the elemental abundances we see across the universe today. When we measure the amount of lithium in one ancient gas cloud and helium in another, their values might not be completely independent. They might still bear the faint billion-year-old signature of having been quantum mechanically linked at birth. This theory pushes the boundaries of cosmology and quantum foundations, suggesting that the first elements are not just a fossil record of temperature and density, but a permanent recording of the universe's transition from a quantum wonderland to the classical reality we know today, a transition that may have left its unique signature on every atom in existence. But to truly push the boundaries of what's possible, we must venture into one of the most mind-bending concepts in all of theoretical physics, the holographic principle. This idea suggests that our seemingly three-dimensional universe, with all its rich complexity, might actually be a projection of information encoded on a distant two-dimensional surface. It's like a cosmic mirage where every event, every particle, and every force we experience is akin to a hologram, a three-dimensional image projected from a flat, two-dimensional screen. While this principle is often discussed in the context of black holes and quantum gravity, its potential implications for the universe's very first moments are staggering, reaching all the way back to the processes that forged the first elements. To grasp how this could influence nucleosynthesis, we need to think about information. In the holographic view, the amount of information, the number of bits or binary digits needed to describe any region of space, is not proportional to its volume as our intuition would suggest, but to the area of its boundary. There's a fundamental limit to how much information can be contained within any given volume of space. Now, rewind to the first few minutes of the universe. The entire cosmos was an incredibly small, dense, and phenomenally hot fireball. According to the holographic principle, this tiny, high-energy domain would have been operating right up against its maximum information capacity. It was a system with a finite number of states available to describe everything within it. This fundamental information limit could have acted as a constraint on the very nuclear physics happening at the time. The process of nucleosynthesis relies on a vast number of possible interactions, protons and neutrons colliding, forming deuterium, which then fuses into helium, and so on. Each of these nuclear reactions, each possible quantum state of a nucleus, requires information to describe it. In a universe bumping up against its information boundary, there might have been a physical limit to how many different nuclear reactions could proceed simultaneously or how many distinct nuclear states could exist. It's as if the early cosmos had a maximum processing power, and the incredibly complex calculations of nuclear fusion were competing for limited computational resources. This could have subtly pruned the possible pathways for element formation, favoring certain reactions over others and potentially altering the final abundances in a way that our standard non-holographic models would never predict. The implications become even more profound when we consider the nature of spacetime itself within this framework. Some holographic models suggest that in such an information-saturated environment, the very concepts of locality and causality, the idea that things happen in a specific place and a specific order, might break down. Two protons might not need to be in the same place to fuse. Their information could interact on the boundary surface, with the result being projected into our three-dimensional experience as a fusion event. This could have opened up reaction pathways that are utterly forbidden in standard physics, allowing for the fleeting creation of exotic nuclear species or isotopes that simply shouldn't exist. Alternatively, the information limit might have suppressed certain resonant states in nuclei, making key reactions like the formation of beryllium-7, a crucial step in the lithium production chain, less efficient, which could directly address the long-standing lithium problem. The holographic principle challenges us to see the first elements not just as a product of nuclear cross-sections and expansion rates, but as the three-dimensional output of a cosmic code being written on a two-dimensional surface at the edge of reality, a code that may have had limited characters available to spell out the recipe for creation. Now, let's shift our perspective from the strange and the speculative to a fundamental assumption that underpins almost all of our models of the early universe, the idea of thermal equilibrium. We naturally picture the primordial soup as a perfectly mixed, uniformly hot bath where every particle has the same average energy, bumping into each other with predictable regularity. This state of balance is the starting point for the standard story of Big Bang nucleosynthesis. But what if that assumption is too perfect? What if the universe was born in a state of dramatic imbalance, and it's precisely this departure from the norm that holds the key to unlocking the mysteries of the first elements? This brings us to the non-equilibrium thermodynamics theory, an idea that suggests the cosmos's first moments were far more dynamic and chaotic than a serene, simmering pot. To understand the power of this idea, imagine trying to bake a cake in an oven whose temperature is wildly fluctuating. You wouldn't get a consistent result. The early universe might have been that kind of unpredictable oven. In a perfect state of thermal equilibrium, particles have a specific, well-defined distribution of energies. But rapid, violent events could have knocked the system out of this comfortable balance. Think of a phase transition, like the moment when free quarks and gluons suddenly confine themselves into protons and neutrons. This wasn't a gentle process. It was likely a turbulent, uneven shift that occurred at slightly different times in different places, creating pockets of plasma with wildly different temperatures and densities right next to each other. Or consider the effect of the universe's own breakneck expansion, which could have simply outpaced the ability of particles to collide and share energy effectively, preventing them from ever reaching a uniform temperature in the first place. These departures from equilibrium aren't just minor details, they can open the door to entirely new physical processes. In a non-equilibrium plasma, you can have a situation where certain high-energy particles become far more abundant than the standard models allow. For instance, there might have been a significant overpopulation of photons in the high-energy tail of the distribution. These aren't your average photons, these are cosmic ray-like particles with enough punch to break apart atomic nuclei as quickly as they form. This could have created a powerful bottleneck, preventing deuterium from accumulating and thus throttling the entire chain of fusion that leads to helium and lithium. Alternatively, a non-equilibrium state might have supercharged certain rare reaction pathways. Perhaps a specific, unusual energy level in a nucleus became much more easily accessible, allowing for the direct fusion of elements that would otherwise be impossible, like beryllium or boron, leaving a unique isotopic signature that the standard model cannot explain. The most compelling aspect of this theory is that it provides a natural, physical mechanism for altering the cosmic recipe without needing to invent new particles or dimensions. It simply asks us to look more closely at the chaotic, violent birth of the cosmos and recognize that it may have never achieved the serene balance we've always assumed. The persistent lithium problem in this view might not be a sign that our nuclear physics is wrong, but that our model of the universe's thermodynamic state is too simplistic. By embracing the chaos and imbalance, we might find that the elements were not forged in a steady oven, but in a frenetic and uneven cosmic kitchen where the final abundances were set not by a single universal temperature, but by the last, fading echoes of the universe's most turbulent and explosive birth pangs. Imagine the fabric of the early universe not as a smooth, blank canvas, but as a complex material cooling and settling into its final form. In much the same way that water freezing into ice can develop cracks and fissures, the universe, as it underwent its early phase transitions, may have developed its own kind of cosmic imperfections. These aren't simple flaws, they are massive, stable structures predicted by particle physics known as topological defects, and they may have been powerful enough to redirect the entire story of the first elements. These defects come in several forms, but the most striking are cosmic strings. Think of these not as tiny threads, but as incredibly dense, unimaginably thin filaments of pure energy, thinner than a proton but with the mass of a mountain range packed into every inch of their length. They would have formed as the universe cooled and various fundamental fields settled into their lowest energy states, much like cracks forming in ice as water freezes. These strings are not made of matter, they are kinks in the very fabric of spacetime itself, and their immense gravitational pull would have been astounding. As they vibrated and oscillated at nearly the speed of light, they would have rippled spacetime, generating powerful gravitational waves. Now, place one of these cosmic strings into the seething plasma of the first 3 minutes. Its presence would have been anything but subtle. The string's colossal gravity would have acted as a powerful tractor beam, violently pulling in the surrounding soup of protons, neutrons, and electrons. This wouldn't have been a gentle accumulation. It would have created raging currents and shock waves within the primordial plasma. In the immediate vicinity of a string, the density of particles would have skyrocketed. This ultra-dense environment would have become a factory for nuclear fusion, far more efficient than the quiet background of the universe. Here, the probability of two particles colliding and sticking would have been vastly increased, potentially allowing for the localized overproduction of elements like helium-4. A region crisscrossed by a network of strings might have ended up significantly richer in heavier elements than the standard model predicts, but the influence might be even more direct than just altering density. The core of a topological defect is a place where the normal laws of physics break down. It's a relic of a higher energy, symmetrical state that existed before the phase transition. Some theories suggest that within the core of a cosmic string or at the junction of domain walls, the fundamental constant, like the strengths of the nuclear forces or even the masses of particles, might be slightly different. It's as if these defects were tiny portals to an earlier, more violent era of the universe. If a nuclear reaction happened to occur inside this anomalous region, the rules would have been different. The energy barrier for fusion might have been lower, or certain unstable nuclear states might have been temporarily stabilized. This could have opened up entirely new pathways for nucleosynthesis, allowing for the creation of minuscule amounts of elements that are otherwise impossible to account for, or providing a mechanism to destroy just enough lithium-7 to solve the long-standing cosmological problem. The truly captivating aspect of this theory is the potential for creating a universe of dramatic variation. Instead of a perfectly uniform elemental abundance everywhere, the early cosmos might have been a patchwork quilt. Vast regions that were largely untouched by these defects would have produced the standard 75% hydrogen, 25% helium mix. But other areas, particularly those near the gravitational wells of cosmic strings or the boundaries of domain walls, would have had a completely different chemical history. When we look out at the oldest stars in the halo of our galaxy, the slight variations we see in their elemental compositions might not be measurement errors. They could be cosmic archaeology, revealing which stars formed from gas clouds that were enriched near these primordial imperfections, and which formed in the quiet, undisturbed voids of the infant universe. The topological defects influence theory suggests that the first elements were not forged in a uniform furnace, but in a landscape dotted with powerful and exotic gravitational anomalies, each leaving its own unique mark on the recipe of creation. This leads us to a theory that asks us to look at the universe not as a collection of particles and forces, but as a system for processing information. We call this the information theoretic approach, and it offers a radically different perspective on why the first elements ended up with the specific abundances we observe. At its core, information theory is the mathematical study of how data is encoded, transmitted, and stored. We use it every day for everything from compressing digital photos to sending messages across the internet. But what if the same principles that govern our digital world also govern the birth of the cosmos? Some physicists propose that the early universe was, in essence, a quantum computer of unimaginable scale, and that the first light elements are the permanent, physical output of its initial processing cycle. The key idea here is that every physical process can be described in terms of information. The position and momentum of a particle, the spin of an electron, the energy state of a nucleus, all of this is information. In the incredibly dense environment of the first few minutes, the universe would have been operating at its maximum information capacity. There was a fundamental limit to how many distinct quantum states could be distinguished from one another within that tiny, hot volume, a concept linked to the holographic principle and the Bekenstein bound. This means the primordial fireball wasn't just a chaotic mess. It was a system with a finite number of bits available to describe everything happening within it. The nuclear reactions that built hydrogen, helium, and lithium were, from this viewpoint, not just random collisions but information processing events. Each fusion reaction was a logical operation, taking the information of two separate particles and encoding it into the information of a single new nucleus. This perspective allows us to ask a fascinating question. Could the specific mix of elements we see represent an optimal or maximally efficient way of encoding the information present in the early universe? Imagine the cosmos had a certain amount of raw data to work with a total number of protons, neutrons, and their initial energy states. The process of nucleosynthesis was the universe's way of compressing and organizing that data. The high abundance of hydrogen with its simple single-proton nucleus could be seen as a basic, efficient data unit. Helium, with 2 protons and 2 neutrons, represents a more complex data structure. The trace amounts of lithium are like the error-checking bits in a digital file, small but necessary for the overall stability of the system. In this view, the elemental abundances aren't accidental. They are the solution to a cosmic optimization problem, the most efficient way to package the information of the early universe into stable structures that could later form stars and planets. This idea extends into the quantum realm with staggering implications. Quantum information theory deals with qubits, which can be in a state of 0 and 1 simultaneously, a superposition. In the first instance, particles would have been in countless superposed states. The act of a nuclear reaction, like 2 protons fusing, would have been a quantum computation that collapsed these probabilities into a definite outcome. The probability of any given fusion reaction occurring its nuclear cross-section might not have been a fixed number based solely on energy, but could have been influenced by quantum information principles like entanglement and superposition. Perhaps certain nuclear pathways were more probable because they represented a more efficient or logical flow of information, a process that minimized computational error or maximized data retention in the evolving cosmic system. The persistent lithium problem might then be reframed, not as a missing amount of lithium, but as the precise amount required for the overall information structure of the universe to remain stable and coherent, a vital piece of code in the cosmic program that eventually allowed for the emergence of complex life. This theory challenges us to see the first atoms not just as lumps of matter, but as the universe's first and most fundamental bits of data, the original code from which all reality was compiled. Now we arrive at a theory that reshapes our entire conception of time and existence, asking us to consider that our universe's grand beginning might have been just one chapter in an eternal, repeating story. We're exploring cyclic universe predictions, a model where the cosmos undergoes an endless sequence of expansions and contractions, a series of big bangs, each followed by a big crunch ad infinitum. In this breathtaking view, the universe is a phoenix, perpetually dying in a fiery collapse only to be reborn from its own ashes. But if this is true, could each new cycle inherit a legacy from its predecessor? And might the primordial abundances of hydrogen, helium, and lithium carry echoes of universes that existed long before our own? The most immediate way a cyclic model could influence nucleosynthesis is through its initial conditions. The Standard Big Bang model starts from a singularity, a point of infinite density where all prior information is presumably erased. But many cyclic theories propose a more graceful transition. Instead of a violent, information-destroying crunch, the universe might undergo a bounce. At the moment of maximum contraction, the incredible density and pressure could trigger a quantum repulsion, a sort of cosmic springboard that launches a new expansion phase. If this bounce preserves even a fraction of the information from the previous cycle, the new universe would not begin with a clean slate. It could inherit a specific particle density, a particular ratio of matter to radiation, or even a preset distribution of energy. This inherited cosmic DNA would immediately steer the process of nucleosynthesis down a different path. A universe born from the ashes of a helium-rich predecessor, for instance, might begin its life with a higher initial neutron count, leading to the production of even more helium in its own first 3 minutes. The elements we see today might not be the unique product of a one-time event, but the latest iteration in a billion-year cycle of cosmic recycling. Beyond simple inheritance, the mechanics of the contraction phase itself could directly sculpt the nuclear abundances. Imagine the universe approaching its big crunch. Galaxies are merging, space is collapsing, and the ambient temperature is rising everywhere. As the cosmos gets hotter and denser, it doesn't just peacefully shrink, it effectively runs the movie of stellar nucleosynthesis in reverse. Stars are vaporized, and the heavy elements forged in their cores over billions of years are broken apart in a process called photodisintegration. Intense gamma-ray photons smash into iron, carbon, and oxygen nuclei, shattering them back into helium and hydrogen. This universal melting pot would gradually erase the complex chemistry of the old cycle, resetting the elemental clock. However, this reset might not be perfectly uniform. The rate and efficiency of this disintegration could vary, potentially leaving behind a specific fingerprint, a slight overabundance of a particular isotope, or a specific ratio of hydrogen to helium that is then carried over into the next cycle. The stubborn lithium problem in our universe might not be an error. It could be a relic, a small piece of nuclear debris that somehow survived the great cosmic recycling process from a cycle long forgotten. Some of the most fascinating cyclic models, like conformal cyclic cosmology, suggest that the laws of physics themselves might undergo a subtle transformation at the moment of the bounce. The constants we hold sacred, the strength of the nuclear forces, the mass of the electron, could be reset to new values each time. In this scenario, the process of nucleosynthesis becomes a universal tuner. Each cycle produces a specific set of elemental abundances based on its unique physical constants. Most cycles might produce universes that are inhospitable, perhaps nothing but hydrogen, or universes that fuse instantly into iron. But occasionally, by sheer chance, the constants will be tuned to values that allow for a rich mix of elements and the formation of long-lived stars. We find ourselves in a universe with 75% hydrogen and 25% helium, not because it's the only possible outcome, but because this is one of the very few outcomes that allows for the existence of beings who can measure it. The light elements become a cosmic barcode, a unique identifier for our particular cycle's physical laws, and a tantalizing hint that countless other universes with different barcodes have come and gone before. This idea leads us to a concept that challenges our very notion of reality, suggesting that the stage upon which the cosmic drama unfolded might not have been a fixed, pre-existing arena, but something that slowly materialized as the universe cooled. We're exploring the implications of emergent spacetime, a radical proposal that the four-dimensional continuum we inhabit, with its 3 dimensions of space and 1 of time, is not fundamental. Instead, it may be a kind of large-scale illusion, a collective behavior that arises from the interactions of countless more basic entities, much like the smooth flow of a liquid emerges from the chaotic jostling of trillions of individual molecules. If spacetime is emergent, then the first instants after the Big Bang were not happening in a pre-formed spacetime. They were the very process of spacetime forming. This transforms our picture of the beginning entirely. There was no first 3 minutes in a classical sense because time itself, as a smooth, flowing parameter, may not have yet fully coalesced. The universe would have been a frothing, chaotic quantum system where concepts like before and after become blurred and where locality, the idea that objects have definite positions, breaks down. In this primordial quantum soup, particles wouldn't have had well-defined locations or momenta in the way our classical intuition expects. Their interactions would have been governed by a more fundamental, non-local web of quantum connections. How would this bizarre, pre-geometric state have influenced the formation of the first nuclei? The entire framework of Big Bang nucleosynthesis relies on classical concepts, particles with definite trajectories colliding in a well-defined, expanding spatial volume. But if spacetime was still gelling during this period, those concepts become approximations at best. The probabilities for nuclear reactions, the nuclear cross-sections that we measure in our modern, cold, classical universe, might have been profoundly different. Without a fixed notion of distance, the electrical repulsion between 2 positively charged protons could have been effectively weaker, as the concept of how far apart they were loses its absolute meaning. This could have made the initial fusion into deuterium drastically easier, potentially supercharging the entire nucleosynthesis process and leading to a universe with significantly more helium and less hydrogen. Conversely, the gradual emergence of a definite time parameter could have altered the perceived expansion rate of the universe. If time itself was crystallizing, the effective clock speed of the cosmos might have been variable, changing how long that critical window for fusion remained open and thus freezing the elemental abundances at a different point. The most captivating possibility is that this emergence wasn't perfectly smooth or uniform. Just as water freezing into ice can develop cracks and imperfections, the crystallization of spacetime from its quantum foundations might have been lumpy. There could have been domains where spacetime achieved a classical character slightly earlier or later than elsewhere. In regions where the classical properties emerged early, nucleosynthesis might have proceeded along the standard textbook path. But in lagging regions still dominated by quantum weirdness, the rules would have been different. Nuclear reactions might have been governed by quantum logic rather than classical probability, allowing for the temporary existence of exotic, unstable nuclear states or enabling reactions through quantum tunneling that would otherwise be impossible. When these domains eventually merged as the universe fully classicalized, the overall mix of elements we see today would be a blend of these vastly different histories. The persistent lithium problem could be the lingering signature of this patchwork emergence, a fossilized reminder that the atoms we are made of were forged before the stage of reality was even fully set, their abundances forever encoding the tumultuous birth of space and time itself. Venturing now into perhaps the most speculative and controversial realm of all, we arrive at theories that bridge the gap between the outer cosmos and our inner experience, the consciousness-cosmology connection. This idea pushes beyond the boundaries of conventional physics to ask a question that is as profound as it is perplexing. Could consciousness itself, the phenomenon of observation and awareness, have played an active role in shaping the physical universe from its very first moments? It's a concept that sits at the far frontier of science, intertwining with interpretations of quantum mechanics that have baffled physicists for a century, suggesting that the observer is not separate from the system but is fundamentally entangled with its outcome. To grasp how this could possibly relate to the first light elements, we need to re-examine one of the strangest aspects of quantum theory, the measurement problem. In the quantum world, particles don't exist in definite states until they are measured or observed. An electron isn't neatly in one place or another. It exists in a cloud of probability, a superposition of all possible positions, until an interaction forces it to choose a single, concrete reality. The famous thought experiment of Schrödinger's cat illustrates this paradox perfectly, with the cat being both alive and dead until the box is opened. The Copenhagen interpretation, one of the earliest and most well-known views, posits that this act of observation is what collapses the wave function, transforming possibility into actuality. Now scale this quantum weirdness up to the entire universe. In its first instance, every particle involved in nucleosynthesis was in a similar state of fuzzy potential. The question then becomes, what or who performed the first measurement that collapsed the wave function for the entire cosmos? Some interpretations, like the participatory anthropic principle proposed by physicist John Archibald Wheeler, suggest that the universe only came into a definite existence when it was eventually observed by conscious beings. In this mind-bending view, we are not just passive inhabitants of a pre-existing cosmos. Our act of observation today is what retroactively solidified the universe's history all the way back to the beginning. Applying this to nucleosynthesis, the specific abundances of hydrogen, helium, and lithium that we measure now were not predetermined. They were one of countless quantum possibilities that only became fixed when conscious life evolved to look back and observe the cosmic microwave background or analyze the spectra of ancient stars. The elemental recipe we see is the one that was compatible with our eventual emergence as observers. Other potential universes with different nuclear outcomes simply never achieved definite reality because there was no one there to observe them. A more radical extension of this idea comes from quantum consciousness theories, which propose that consciousness isn't a mere byproduct of brain activity, but a fundamental feature of the universe akin to space and time. If consciousness is a primary component of reality, then it would have been present in some nascent form even during the Big Bang. This doesn't mean thinking thoughts. It could be a proto-consciousness, a fundamental quality of existence that interacts with matter. In this scenario, the act of observation that collapsed the quantum wave functions of the early particles wasn't done by humans billions of years later, but was an intrinsic process within the universe itself. The dance of particles during nucleosynthesis would have been a co-creative process between matter and this underlying consciousness field, potentially guiding nuclear reactions toward outcomes that would later allow for complex life and full self-awareness. The precise fine-tuning of the constants that allowed for a life-giving mix of elements might not be a staggering coincidence, but rather evidence of a universe whose physical laws are intertwined with the potential for mind from the very outset. It is crucial to emphasize that these ideas reside far outside the mainstream of physics. Critics rightly point out the immense challenge of testing these proposals empirically. They argue that invoking consciousness as a causal agent is a departure from the methods of physical science and veers into the realm of philosophy or metaphysics. The standard response is that the apparent fine-tuning can be explained by other means, such as the multiverse, without needing to resort to such speculative connections. Yet, the consciousness-cosmology connection persists as a captivating, if controversial, pillar of thought. It represents the outermost limit of our curiosity, a place where science meets deep mystery, forcing us to confront the possibility that the story of the atoms in our bodies is not just a tale of forces and particles, but is inextricably linked to the very act of our own perception, weaving consciousness into the fundamental fabric of cosmic history. Finally, we reach the outermost edge of speculation, a theory that reframes our entire reality not as a fundamental existence but as an advanced construct. This is the simulation hypothesis, and its implications for the origin of the first light elements are as profound as they are controversial. The core idea is startlingly simple. What we perceive as the universe might not be base reality, but an incredibly sophisticated simulation, akin to a hyper-realistic video game running on some form of computational substrate in a higher-level reality. If this is true, then every law of physics, every constant, and every event in cosmic history, including Big Bang nucleosynthesis, is not a discovery of fundamental truth, but an observation of the rules programmed into the simulation. From this perspective, the process that forged hydrogen, helium, and lithium takes on a completely new character. The parameters governing nucleosynthesis, the strengths of the nuclear forces, the mass of the electron, the expansion rate of the universe, would not be immutable laws discovered through science, but rather variables set by the programmers or simulators. The astonishing fine-tuning of these constants, which allows for a universe rich in complexity and life, could be explained not by an infinite multiverse or a divine creator, but by intentional design. The specific, life-allowing abundances of the light elements we measure would be the default settings chosen for this particular simulation run. The long-standing lithium problem, the small discrepancy between prediction and observation, might not be a puzzle to be solved by better physics, but a deliberate feature, a rounding error in the code, or even a subtle clue left by the designers to hint at the artificial nature of our reality. Some researchers, like Oxford's Nick Bostrom, have argued that if a civilization could ever reach a technological level capable of running ancestor simulations, high-fidelity recreations of their own history, then the number of simulated minds would vastly outnumber the minds in the original base reality. Statistically, we ourselves are more likely to be among the simulated beings than the original ones. In this framework, the light element abundances become a potential piece of forensic evidence. If we were to discover that the values are too perfect, that they are optimal for life in a way that seems analytically designed rather than emergent from chaotic processes, it could be interpreted as evidence for the hypothesis. Conversely, finding a seemingly arbitrary or inefficient value like the lithium discrepancy could also be telling. It might represent a computational shortcut, a necessary simplification to make the simulation computationally tractable on whatever unimaginable computer is running it. It is crucial to state that the vast majority of scientists do not consider the simulation hypothesis to be a scientific theory in the conventional sense. Its primary criticism is that it is arguably unfalsifiable. There is no conceivable experiment we could run from within the simulation to definitively prove we are in one, as any result could be explained as part of the programming. However, its power lies not in its testability, but in its philosophical challenge. It forces us to confront the nature of the laws we study and asks whether the quest to understand the first 3 minutes is a journey to discover fundamental truth or an exercise in reverse engineering the source code of our own existence. The first light elements in this ultimate speculation are not ancient fossils but the foundational lines of that code, the initial parameters that booted up the cosmos and set in motion everything that would follow, from the first stars to the conscious minds that now look back and wonder how it all began. From the solid bedrock of Big Bang nucleosynthesis to the mind-bending possibilities of the simulation hypothesis, our journey through these 30 theories reveals a breathtaking truth. The story of the universe's first light elements is far from a settled chapter. It is a living, breathing frontier of science where each idea, whether grounded in decades of observation or soaring on the wings of pure speculation, offers a unique window into those first frantic moments of existence. We've seen how the slightest tweak to a fundamental constant, the faintest whisper of a quantum fluctuation, or the briefest existence of a primordial black hole could have entirely rewritten the cosmic recipe, leaving us with a universe unrecognizable to our own. These aren't just abstract intellectual exercises, they are different versions of reality itself, each with the power to determine whether galaxies, stars, planets, or even us could ever come to be. What unites this incredible diversity of thought is a shared, profound curiosity about our origins and a relentless drive to make sense of the clues left behind. The primordial abundances of hydrogen, helium, and lithium are more than just numbers on a page. They are a cosmic fingerprint, a billion-year-old message from the dawn of time. Deciphering that message requires every tool we have, from the colossal particle colliders that recreate the conditions of the quark-gluon plasma to the space telescopes that scan the ancient light of the first stars for the faintest anomalies. Every new observation, every more precise measurement of the cosmic microwave background, and every discovery in a subterranean neutrino lab acts as a test, gently guiding us toward which theories might hold a piece of the ultimate truth and which must be set aside. This process is the very engine of science, a collaborative effort spanning generations to answer the most fundamental questions we can ask. So, as we reach the end of this exploration, the conversation doesn't stop here. We want to hear from you. Which of these theories captured your imagination the most? Does the elegant simplicity of the Standard Model feel the most compelling, or are you drawn to the chaotic beauty of the inhomogeneous universe? Perhaps the quantum weirdness of space-time foam or the cosmic grandeur of the multiverse speaks to you. Share your thoughts in the comments below. Let's continue this incredible discussion together. If you enjoyed this deep dive into the origins of everything, make sure to subscribe and hit the notification bell so you don't miss our next journey to the frontiers of space, time, and understanding. The universe is full of mysteries, and together we can continue to unravel them.